Bismillah Productions presents Physics Out of the Box. My name is Tariq Ali, and like the title says, have we discovered the fabric of reality? Well, we most definitely think so. At the end of this video, we'll be presenting the proof that we have so far to back up our theory. So what is the fabric of reality? In a nutshell, it's vacuum space and quantum information. What exactly do we mean by vacuum space and quantum information? To understand what they are, we need to understand how we got here. Ever since Albert Einstein, it has been understood in the world of physics that understanding gravity is the key to unlocking the theory of everything. So you would expect that if you happened to stumble upon the theory of quantum gravity, it should be accompanied by a stream of solutions to major scientific problems. And that's exactly what we have. When we apply this particular solution to the gravity problem, it's going to sound as though we're exaggerating, but here's a list of things that we started getting solutions to. We started getting solutions to the biggest problems in the scientific world. For example, dark energy, dark matter, the fundamental workings of gravity, the vacuum catastrophe, gravitational time dilation, the curvature of space, what is the fuel of the atom, what is vacuum space at the quantum level, and what is reality at its most basic level. All this sounds too good to be true. But this is exactly what's been predicted by physicists for over a century. The theory of quantum gravity is the key to the theory of everything. So if you have the theory of quantum gravity without an accompaniment or an avalanche of new solutions, then your theory cannot be correct. But if you're getting solutions to long-standing physics problems, then you know for certain that you're on the right track. So let's start at the beginning. The search for the cause of gravity. Albert Einstein took a giant leap forward when he made the conclusion that gravity was not a force, but the effect of acceleration. So what's the difference between a force and acceleration? So far, we are aware of only three forces other than gravity: the strong nuclear force, the weak nuclear force, and the electromagnetic force. Each of these forces has an associated particle responsible for that force. The gluon is responsible for the strong nuclear force, the WZ bosons for the weak nuclear force, and photons for the electromagnetic force. These force particles exert their force by completing a cycle. They start at A, they go to B, and they come back to A. The return to the starting position is the hallmark of all particle forces. One of Albert Einstein's thought experiments explaining gravity was a man in a rocket ship and a man on the ground. He asked himself if there was any experiment the man in the rocket ship could do that would tell him if he was on Earth or in a rocket ship? And the answer to that was no. So the rocket ship is accelerating at 9.8 meters per second squared. And the man on Earth is going down at 9.8 meters per second squared. So both of these people, they have the exact same force on them. They are both heading towards the ground, or the base of the rocket, or the ground, at exactly the same speed. So Einstein concluded that because the rocket ship is going up and the ground is pushing against the man, he concluded, and that causes 1g. You get 1g. He concluded that the Earth was moving up at exactly 1g. Just like the rocket ship. So Albert Einstein concluded that the falling object was not actually falling. Like the man in the spaceship, he's falling, but it's the spaceship that's actually accelerating, and it seems as though the man is falling. So Albert Einstein concluded that the man here is falling because the ground is moving up at 1g. Although this solution answered a lot of questions, it also came with a few problems, like the curvature of space. No one can explain exactly what the curvature of space actually looks like, or why it should occur. I'm sure that you've heard this answer regurgitated every time the question arises, but never understood and never explained. The explanation that a falling object is not actually falling, but it is the ground that is moving towards the object at the speed of 9.8 meters per second squared, cannot be true. Why? If that were the case, we would see the Earth getting bigger, but we don't. For example, we have the Earth, and we have people on the Earth. We have people here, we have people here, we have people here, and of course we have people here. Now, if the ground is moving up here at 1g, here at 1g, here at 1g, and of course here at 1g, then you can see we have a problem, because the ground will be moving up in all directions, in 360 degrees of the Earth, in wherever wherever a person is, the ground is moving up at 9.8 meters per second squared. That would mean that the earth would have to get bigger. Every second, for the first second, it will get bigger by 10 meters in all directions. In the second second, it will get bigger by 20 meters in all directions. In the third second, by 30 meters. And the increase will keep on speeding up. But observations tell us that that's not happening. The other reason why this cannot be happening is that gravity weakens at higher altitudes. For example, if a man is on the earth, or a man is at 2,600 kilometers in altitude. The man at 2,600 kilometers in altitude will feel gravity, but he will only feel half the gravity that the man on the ground feels. So this man will feel 4.9 meters per second squared. And this man will feel 9.8 meters per second squared. Now these both feeling gravity in the same horizontal position. If the earth was moving up at 9.8 meters per second, then it would move up for both of these people. The person at 2,600 kilometers and the person on the ground would both feel the same movement of the ground. But the man in the high altitude only feels half g, whereas the man on the ground, he feels 1g. So these kind of things tell us that the theory is almost there, but not quite. It's a bit like the king has no clothes. It took an innocent little boy to make the people realize the obvious. The king has no clothes. It should be noted that the king here is the solution, not the author. We also hear that vacuum space curves near a massive object. But what does that look like? And of course, why should it curve? So what is the explanation to gravity? The explanation is even stranger and more fantastic than even the theory of quantum physics. In the years since Albert Einstein, there's been a number of discoveries. For example, Stephen Hawking and Hawking radiation. It was always understood that a black hole can never die. Stephen Hawking said that a black hole emitted radiation. This radiation is named after him and is called Hawking radiation. It turns out that vacuum space is full of something called the quantum froth. This quantum froth is particles being created and destroyed. Particles always appear with their antimatter counterparts. For example, an electron will have its counterpart, the positron. So as soon as the particles have been created, they come back together and they annihilate each other, except at the event horizon of a black hole. So you have a black hole, or the event horizon of a black hole, and at the edge where the event horizon starts, right at the edge, you have two particles being created. One a matter particle and the other one is an antimatter particle. The effect of the black hole is such, or physics is like this, that the antimatter particle will be attracted to the black hole, and the normal matter particle will escape. So the normal particle will show up as Hawking radiation, and the particle that goes into the black hole, this will go in and it will cancel or eliminate a particle like itself, but the opposite of itself. This effect has a lessening of mass. Because one particle has disappeared from the system, the black hole becomes a little bit smaller than before. So what's happening is particles are appearing from vacuum space. Seemingly nothing. Two particles are appearing. One is making the black hole smaller than before, and the other one is showing up as Hawking radiation. Then there's the quantum field theory. In this theory, vacuum space has at least 17 different energy fields. Each energy field is responsible for a particular fundamental particle, likes of the famous Higgs field, which is responsible for the Higgs boson. In fact, there's a different field for every different fundamental particle. The theory says that every cubic centimeter of vacuum space has a specific amount of energy because of these fields. So how much energy does it actually have? Well, according to their calculations, there's an upper limit of, wait for this, it's 10 to the power of 112 ergs. 10 to the power of 112 ergs per cubic centimeter. So exactly how much energy is that? Well, we did some calculations, and the answer is really astronomical. Well, at least the numbers are. According to quantum field theory, there's more energy in every cubic centimeter of vacuum space than the total output of the sun over a period of 1,000 years. On this note, I would request you to do your own calculations and let me know in the comments exactly how much energy there is in 10 to the power of 112 ergs per cubic centimeter. Observations, on the other hand, only show 10 to the power of negative 8. 10 to the power of negative 8. So 10 to the power of negative 8 ergs per cubic centimeter. And that's what's known as the quantum, not the quantum, sorry. That's what's known as the vacuum catastrophe. Why is it called the vacuum catastrophe? Well, there's a difference in theory and observation by a factor of 120 orders of magnitude. This, in fact, is the biggest disparity between theory and observation in the whole of the scientific world. And then there's Edwin Hubble and his expanding universe. Edwin Hubble discovered that the universe was expanding in all directions. Professor Soule and his colleagues in 1998 did some precise measurements in the hope of seeing a slowdown in the expansion of the universe. On the contrary, they discovered that not only was the universe still expanding, but the expansion was in fact speeding up. So the strangest thing about this phenomena of the expanding universe was that the objects themselves, the galaxies that seemed to be moving away, were not actually moving. It was the space in between the galaxies that was getting bigger. So why? Why was the space in between the galaxies getting bigger? And why do we know that? Scientists have concluded that there must be an energy that is causing the space in between the galaxies to get bigger. It turns out that for every megaparsec, 1 megaparsec is approximately 3.2 million light years. The universe was expanding at the rate of approximately 70 kilometers per second. And that's everywhere. Wherever there's two galaxies sufficiently apart from each other that they don't have a gravitational lock on each other, the space in between them will be increasing by approximately 70 kilometers per second. It turns out that there are galaxies out there that are moving away from us at faster than the speed of light. And you may not be aware, but any particle that has mass can't approach the speed of light, never mind exceed the speed of light. So from the evidence, we have realized that the space in between is expanding and the galaxies themselves are standing still, basically. And this mysterious energy has been named dark energy. Dark energy is responsible for the expansion of space. So these discoveries, since Albert Einstein, have given us a second and more feasible solution to the gravity problem. Albert Einstein's solution was that the ground was moving up, like in this drawing. And we realize there's a lot of problems with the ground moving up. But because of these discoveries since Albert Einstein, we now have a second and more feasible solution. We can have the fabric of space moving downwards at the rate of 9.8 meters per second squared. Why? Why is that? Because we have realized that vacuum space has its own set of properties, meaning that vacuum space is not nothing. Vacuum space is actually something. First property: one volume of space can move independently of another volume of space, like in the expanding universe. The second property: vacuum space has a specific amount of energy per cubic centimeter. Third property: vacuum space can create virtual particles. And not only virtual particles, but actual real particles from seemingly nothing, in the example of Hawking radiation. So vacuum space is something as opposed to nothing. If the fabric of space were to be accelerating towards the Earth at 9.8 meters per second squared, so let's say we have the Earth, and from all directions the fabric of space was moving towards the Earth at a rate of 9.8 meters per second squared. This would give us the gravity that we're looking for, without going against any of the laws of physics. But we have a problem. We have an energy surplus. In fact, we have quite a big energy surplus. That energy is inside that space that is moving towards the center of the Earth. So, what happens to that energy? So gravity is often called negative energy. This is a bit like saying that my car engine produces negative energy. If I complain to my mechanic that my engine is producing negative energy, he'll ask me how I came to this conclusion. So I explain. Whenever my engine is running, the negative energy created by my engine affects my fuel tank, and my fuel tank starts to empty. So the engine must be producing negative energy, which affects, obviously, the energy in my fuel tank. So the mechanic would reply that it's your engine that is consuming energy. And the energy in your fuel tank is the energy that your engine is consuming. In other words, what we meant by negative energy is that it's consuming energy. So negative energy is another way of saying energy has been used. And as we know, mass produces negative energy. In other words, mass consumes energy. So how do we understand, how can it be consuming energy? Well, every atom has neutrons and protons. They're very much alike. So we'll concentrate on just one particle, the neutrons. The neutrons have a mass, and they also produce negative energy. Now, it's very interesting to understand that the individual parts of the neutron, the two down quarks, the one up quark, and the gluons responsible for the strong nuclear force, only account for 2% of the mass of the whole neutron. So let me say that again. If you were to get a neutron, break it up and weigh the parts separately, the total weight or the total mass of all the parts of the neutron would only weigh 2% of the mass of the whole neutron. So if the parts of the neutron only weigh 2%, where is 98% of the mass of the neutron coming from? It turns out that 98% of the mass of the neutron is being produced from the interaction between the quarks and the strong nuclear force. The quarks are trying to escape the confines of the neutron, but the strong nuclear force, on the other hand, is hell-bent in keeping them inside. So there we have the neutron. We have the quark, two down quarks, one up quark, and the strong nuclear force. So the neutrons, the quarks inside the neutron, they want to escape. Whereas the strong nuclear force wants to keep them inside the neutron. This interaction between the quarks and the strong nuclear force is so mind-bogglingly intense that it is responsible for producing mass. In fact, it produces 98% of the mass of the neutron. So, as we know, where mass is being produced, energy has to have been consumed. Albert Einstein has given us the most famous equation ever. E equals mc squared. So E equals mc squared. So if you want to find out how much energy this mass needs or is equal to, you multiply it by speed squared and you get an idea of how much energy is in that mass. So if 98% of the mass is being created, it means an extremely large amount of energy has to have been consumed. That's physics for you. Also because of the presence of negative energy. So the proton is consistently producing negative energy. It's producing mass, we know this. It's producing negative energy, we know this. And we also know negative energy is another way of saying energy has been used. So where is this energy coming from? Let's say, on the other hand, you will find people saying that it doesn't need energy constantly. So let's say you have a particle. You have a particle and it's speeding at almost the speed of light. It will need energy. You will need to input energy to speed it up to that speed. There will be an increase in mass, but no more energy will be needed to keep it at that mass. Unless you wanted to change directions, or in the case it comes against an obstacle. The quarks inside the neutron have their directions being changed at a truly insane frequency. This change of directions requires energy. And it requires an extremely large amount of energy on a continuous basis. The neutron is creating mass, but at the same time, it's creating negative energy, the smoking gun. Negative energy is the smoking gun. That energy has been consumed. There's no way to get around that. So, where is this energy coming from? So let's go back a little bit. On one hand, we have a surplus of energy because vacuum space, the fabric of space, is moving towards the Earth. And the energy that was in that space has suddenly vanished. When the vacuum space keeps on moving, the energy in that vacuum space also keeps on coming into the Earth. But it keeps on disappearing. And on the other hand, we have negative energy produced by mass, also known as gravity. So we can safely say that the energy we thought was surplus is in fact the energy that fuels the atom. Mass needs a continuous stream of energy to sustain itself. And gravity is the effect of the whole system. It's a bit like a firestorm. If you have a firestorm, let's say you have a huge fire. when we have a fire, the fire consumes oxygen. And the bigger the fire, the more oxygen is being consumed. So the oxygen gets consumed, and more oxygen needs to rush in and replace the oxygen that's been taken out of the system. And the whole system requires oxygen coming from all directions. If the fire is big enough, you'll get so much oxygen rushing to the fire that it will seem like a storm. So one thing with this phenomena is close by the fire, the speed of the wind is a lot more than, let's say, further away. Let's say there's a man here and there's a man here. The man here will feel high speeds of wind. The man here won't feel the high speeds of wind, but he will feel that the wind is flowing, but in a lesser amount. So that's a bit like the earth and its gravity. So because the fire is consuming oxygen and the replacement oxygen is causing the firestorm, just like that, the fabric of space is accelerating towards the earth. It's accelerating towards the earth, and close by the earth, you will feel the speed of the fabric of space more than you will feel further away from the earth. And that's exactly what we have in this example. At 2,600 kilometers, the gravity is exactly half, and at ground level, the gravity is 9.8 meters per second squared. So this model explains a lot of things that the previous model didn't explain. So the ground moving up was giving us a lot of problems, whereas the space coming down is solving those problems. The earth doesn't need to get any bigger, and the gravity can be different at low altitudes and at high altitudes. It answers the problem of the fuel of the atom. So from our understanding, the fabric of space must be divided into cells of space. These cells of space, they have a specific amount of energy. They receive information and they light up like a pixel on a television screen. We see this lighting up process as a particle. This lighting up process consumes the energy from that particular cell of space. when the energy is completely finished, the last thing that cell does is it sends its information to the nearest cell closest to it. And that cell lights up and produces the exact same particle. So the first cell has depleted all its energy and it disappears, leaving an empty place for another cell to move into. That is how the flow of space results in gravity. When we look at gravity like this, then we can understand the flow of space is why space seems to curve. For example, let's say this is the sun and this is the earth, and a star, let's say behind the sun, the star behind the sun is shining light. So it's shining light in all directions, and it's shining light close to the sun, but the space that's moving towards the sun makes that light bend towards the earth. This is what we see as the curvature of space. So we're seeing a lot of questions being answered. We understand why gravity causes time dilation. It's because space is moving. We also understand the vacuum energy catastrophe. It's because energy in vacuum space is of a type of energy that doesn't actually consume energy, and thus does not create gravity. Because gravity is what we use to measure how much energy there is in empty space. And we start to understand what fuels the atom. The atom needs energy. Where is this energy coming from? It's coming from the fabric of space, vacuum energy. We understand that space needs to be quantized and works like pixels with their own energy. We understand that space cells need information to produce particles, and together they are the building blocks of reality. So all that is well and all that is fine. But where's the proof? How can we prove this?